We hear about averages all the time, right? The average salary, the average test score, the average temperature. But what if I told you that the average often hides the most interesting, the most important part of the story? Today, we're going to dive into this idea of statistical variability and see why the spread of the data is often way more telling than its setup.
Okay, let's just jump right in with the little puzzle. Imagine you've got two cities, and both have an average annual temperature of, say, 60 degrees Fahrenheit. So, same climate, right? Well, not so fast. One city could have really mild winters and nice cool summers. The other could have brutally freezing winters and then scorching hot summers. The average comes out the same, but living there, a completely different experience. That difference, that's variability in a nutshell.
And this visual just nails the point. Look on the left at the distribution of adult heights. See how all the data points are kind of huddled together, clustered really tightly around that average of 70 inches? Now look over at the right at adult weights. The average is 170 pounds, but whoa, look how much more scattered and spread out that data is. They have the same kind of center, but they tell completely different stories. An average by itself just can't capture that.
So, this brings us right to our first big idea, why we absolutely have to look beyond that simple average if we want to truly understand what a set of data is telling us.
Okay, so the official term for this spread we keep talking about is variability. It's really just a number, a single quantitative number that tells you how scattered or how clustered your data is. I mean, if every single score was identical, you'd have zero variability. But if your scores are all over the map, well, then your variability is really high.
So why do we even bother to measure this? Well, it does a couple of really crucial jobs for us. First, it helps us describe the data. Is it tight and consistent, or is it wide and diverse? And second, it tells us how well that average actually represents the whole group. If you have low variability, that average is a pretty trustworthy guide. But with high variability, that same average can be super misleading. It's really all about measuring consistency and predictability. Okay, so we're all on board. We need to measure this spread. But how? How do we actually do it? This next part is kind of a quest to find the best statistical tool for the job. And we're going to explore this in 3 steps, kind of building up from the most basic, simple idea to the most powerful and widely used tools out there. We'll start with the range, then move to variance, and finally land on the big one, standard deviation. So our first attempt is the range, and it's super simple, right? You just take the highest score you've got, subtract the lowest score, and bam, that's your range. The problem? It's pretty crude. It's an unreliable measure because it only cares about 2 extreme values and completely ignores everything else that's happening in the middle. Right, so that's a huge weakness. We need a better way, a more robust method. We need a measure that takes every single score into account to give us the real picture of the spread.
Now, the most obvious next step seems simple, doesn't it? Let's just find the distance of each score from the mean and then average all those distances. Makes sense. But when statisticians tried this, they hit this frustrating dead end. The positive distances and the negative distances, they always perfectly cancel each other out. You always wind up with 0. It tells you absolutely nothing. So how did they solve this problem? Oh, it was a beautifully simple and clever trick. Before you add up all those distances, you just square each one. Squaring a number always makes it positive, right? So now they no longer cancel each other out. It's the key that unlocks the whole thing. And the result of that process gives us our second measure, variance. It is, quite literally, the average of all of those squared distances from the mean. It's a much more stable, much more informative measure than the simple range. And hey, don't let the symbols freak you out for a second. The concept here is way more straightforward than it looks. All you're doing is taking the sum of all those squared distances we just made, statisticians call this the sum of squares, and then you divide by the number of scores you have. That's it. You've just calculated the variance. But there's one little problem. Because we squared the distances, our units are now all weird, like inches squared, which isn't very easy to wrap your head around. So we do one final step. We just take the square root of the variance, and that gives us the standard deviation, our absolute gold standard measure. It brings the units back to normal, like regular inches or pounds, and gives us a number that represents the standard or typical distance from the mean. Now, just when we think we've got it all sorted out, the real world throws a curveball at us. See, most of the time in research, you can't measure everyone, the entire population. You have to work with a smaller piece, a sample, and this creates a really tricky problem. And here's the heart of the issue. Samples almost always look less varied than the full population they come from. It kind of makes sense when you think about it, right? If you take a smaller group, you're just less likely to grab the most extreme high and low scores. This means our formula, as it is right now, is going to give us a biased answer. It's going to consistently underestimate the real variability.
So statisticians came up with another clever fix. Just look at the two formulas here. See the tiny difference in the denominator, the bottom part of the fraction? Instead of dividing by n, the total number of scores, for a sample we divide by n minus 1. It seems like a small change, but this little tweak mathematically corrects for that underestimation bias. It inflates the number just enough to give us a much more accurate picture of the variability in the whole population.
Okay, so we have these powerful tools. Let's wrap this up by looking at how they're actually used to describe data and, make real discoveries.
And here you can really see it in action. The mean is right there in the center at 80. The standard deviation then acts like a yardstick around that central point. With a standard deviation of 8, we get a really clear visual sense of how far a typical score tends to fall from that average. It makes the idea of spread into a concrete distance.
So to kind of put a bow on it, our two key measures have slightly different day jobs. Standard deviation is our main descriptive tool. It's what you'd use to talk about the spread of heights or weights we saw earlier. Variance, though, that's the real engine of inferential statistics. It's what researchers use to figure out if a pattern they've found is a meaningful discovery or if it's just random noise, what they call error variance.
All right, we've been on quite a journey, haven't we? From a simple question about cities to some pretty powerful statistical tools. Let's lock in all that learning and just boil it down to the key takeaways.
Okay, here's what you really need to remember. First, the average alone is not enough. It only tells part of the story. Second, variability is the tool we use to measure the spread or consistency. Third, standard deviation is the most common and useful measure of that spread. And finally, and this is a big one, if you're working with samples, you have to use that special n-1 correction to get an unbiased, accurate estimate.
So, I'll leave you with this question. The next time you see a headline or a report about the average income or the average performance of something, you'll now know to ask the much more important, much smarter follow-up question. Yeah, but what's the variability?